Assalamu alaikum. Welcome to lecture 25 of natural language processing. This is most likely going to be our last week of lectures. Uh, so, today we will wrap up our discussion on machine translation. We had started talking about machine translation in the last lecture, and we had introduced the encoder-decoder model, which is popularly used for solving machine translation problems. And so today we'll wrap up machine translation with discussion on its evaluation and a few other things regarding practical machine translation. And then we will start with contextual embeddings and bidirectional encoders using transformers or BERT. So which is chapter 11 of your textbook. So we will discuss that next. So that is basically the agenda for today. So I think let's get started then. So we had started talking about evaluating machine translation or MT evaluation. So as in most NLP evaluation tasks, most NLP evaluations, you have two main categories of evaluation. One is, of course, human evaluation, and the other is, of course, automatic evaluation. So human evaluation is often required for high quality work because that would give you a more accurate measure of the quality of the performance. But automatic measures are also used frequently, and for quick evaluation, automatic measures are preferred. So we had already talked about human evaluation. Typically, they evaluate along two dimensions, adequacy and fluency. And for both of these dimensions, you have some scale, and then you give annotators or evaluators the data that you want to evaluate, as well as the scale and some description of how to evaluate. And then you get those scores from the evaluators or annotators, and then analyze those scores to generate a final assessment of the evaluation. But today we are going to talk more about the automatic. So in automatic, again, there are two broad categories. One is based on overlap, word or character overlap, word or char overlap. And the other is based on similarity. So overlap, of course, as the name suggests, is exact match, and similarity is inexact match. But within that similarity category, you have some prediction-based techniques as well. So let me first start with one measure which is popular for evaluating machine translation, which is called BLEU. So which basically stands for bilingual bilingual evaluation and study. So this is a precision-based measure that was proposed primarily for evaluating machine translation. And so in machine translation evaluation, you have a candidate C, which is the generated translation. And then you have reference R, which is the true translation. And there could be more than one such true translation. So references could be in general more than one. So there may be more than one way of capturing the information of the source language, and those more than one correct way of capturing the information in the source language, those are captured in the R. And as I said, R may contain more than one sentence. So let's take some simple examples. Let's say we have an R. So the cat sat on the mat. Okay. So this is a correct translation. And another correct translation could be cat is on the mat. If D भी निकाल लेता हूँ, cat is on the mat. So these are correct translations. These are references. And of course, your machine translation algorithm would give you the candidates, and they could be anything, of course, depending on your model. So for example, one could be simply the cat. So this could be an output, and we would like to determine whether the cat is a correct translation given the two references that we have, the two correct translations that we have. So this is the idea of evaluating in machine translation. So now let's specifically look at the BLEU score. So as I said, this is BLU is precision based. And what does precision means? We are conditioning or normalizing over the words in the generated text in the candidate. And we are seeing how many of those words actually appear in the reference. So that's precision. The output is the focus. And of course, we are mapping or matching with the reference. So precision based and also usually word based. It's not character based. The traditional BLEU is word based, meaning that we match words. And then of course, it is based on n-gram. So of course, the simplest case would be unigram matching. And some other concepts, of course, we'll be discussing this. It uses the idea of clipped precision, as we will see. Precision is bounded. And then it also uses the notion of what is a brevity penalty. Okay, so let's discuss this with an example. Okay, let's start with the simplest scenario. Of course, for higher n-grams, it will be similar. So let's talk about unigram, blue, which is sometimes also called BLEU-1, meaning that 1 gram. So let's say the candidate that we have, and I will basically let me, this is the reference. And let's say my candidate is, of course, the cat. So we'll consider all the words in the candidate. In this case, there are two words, there are two unigrams. So unigrams are there the, and the other is cat. So we will now find whether the appears in the reference. So the appears in the reference, so that's one. Cat, does it appear in the reference? Any of the reference. So there are two references. They can appear in any of them. So cat also appears. So this, in this case, you have both unigrams appearing in the reference. So your precision would be 2/2, which would be 1. Okay. So for this particular example or test example, we have a precision of 1. So let me take another example. Let's say we have the, and the, and then let's say cat. So we have generated 3 words, the, and then cat. So of course, now we have 4 unigrams, the, and cat. So this is where you get the idea of clipped precision. So in this case, you have 4 Ds, and each of those Ds appear in the reference. So there is a D in the reference. There's also a cat in the reference. If I use the previous approach, I would again get 4 over 4, which is 1. But this, as you can see, this is a bad translation. You have one word repeated multiple times. So the clip precision basically clips the word that is repeated to the maximum number of times that that word appears in any one of the reference. So for example, if you look at D, so D occurs maximum twice in one reference. D cats sat on D mat. So there are 2 D there. So in the generated text, we can only thus consider 2 of these Ds, and we cannot consider the other 2. Okay? So the maximum number of Ds that appear in any reference is 2. So this is basically the clipped precision. So what do we have? So we only consider 2 of those. So we have 2 for D, and then of course we have 1 for cat. Okay? एक सेकंड कितना था? So there are 3. So 4 of 4. Okay? So there are 3 of them, so we'll only consider 2 of those. Okay? And then of course the precision would be now 3 over 4. So this precision is called the clipped precision. And in Bleu Score, we compute always the clipped precision. We only consider a particular word to the maximum extent that appears in any particular reference. In this case, we are considering D. So D, even though it appears 3 times in the precision in the output, we only consider it twice because that's the maximum number of times that it appears in any one reference. Okay? So, of course, when you are evaluating any machine translation system, you are evaluating multiple examples, not just one example. So this is just one example. You will have multiple examples. So you will get a precision or a clip precision for each of those examples. So usually we combine all of those to get one value using the geometric mean. Of course, there are slight differences in application, but the typical usage take the geometric mean. So what is geometric mean? You multiply all the precisions and take the nth root. If you are multiplying n values, then you take the nth root. Okay? So, so for example, let's say मेरे पास एक और example है reference उसका मैं लिखता हूँ. It is, let's say, freezing outside, and let's say candidate is, let's say, cold outside. Okay? So of course, in this case, the unigram precision would be what? So only outside matches. So 1 over 2. ठीक है ना? So ये second sentence का 1 over 2 हो गया. Overall blue क्या होगा? Overall blue is, as I said, the geometric mean. It would be, what was that? 1.2, 0.5 into 0.75, and the square root of this. Overall, this would square root. So square root would be around 0.12. Sorry, point. So you have to take the square root. Let me write it here, SQR2. I don't know if square root automatically calculate होगा कि नहीं होगा. Okay. So this is the square root. This is the final precision or the Bleu score for the entire corpus that you are evaluating, which in this particular case had two examples only. But in addition to this, the Bleu score also uses another concept which I mentioned earlier, which is called the brevity penalty. So the brevity penalty basically penalizes outputs that are small, because whenever an output is small, artificially the precision would be large. So let's say if you have an output simply D, so let's say candidate is D. So there is just one output, and one output matching would be relatively easy. So you get a precision of 1/1. So it penalizes outputs that are small. So how does it do that? It, after computing the entire Bleu for the entire corpus, it multiplies that Bleu with a brevity penalty. And the brevity penalty is computed, let me write the formula first in this way. Exponent is the E, E, 1 minus R over C. Of course, this R is actually the length of the reference. So ऊपर मैंने R और C actual reference और C के लिए use किया, तो let me use a small case. So C, of course, small c, length of candidate, R is the length of reference closest to C. So this is the case for when you have multiple references. जब आपको 2-3 references हैं, तो आपने वो वाली length लेनी है जो closest है C के साथ. So this is one way. Of course, some other authors use the smallest one, but this is the more common one, where you use R as the length that is closest to the generated text. ठीक है? So so in our case, let's say जो मेरा reference था, so the cat sat, एक second, 3, so this is 6, so this is 4. So let's say मेरे पास candidate था the cat, ठीक है? So now this candidate is 2, meaning that C is 2. इसके लिए जो reference हम use करेंगे वो 4 use करेंगे, because 4 is closest to 2, not 6. ठीक है? And then of course EXP would then become 1 minus, so reference is 4 divided by 2. So this is not computing. So basically you can see that if it is both the reference and candidate are of the same length, then the exponent is of course 0, which means that this is going to be 1. There is no penalty. By the way, this penalty is only applied when R is when C is smaller than R. It is not applied when C is greater than R. Remember, it's brevity penalty. It's only applied when C, the length of the candidate, is smaller than R. Okay? And then you multiply our overall Bleu. So overall Bleu would then be brevity penalty into geo mean of clipped precisions. Okay? By the way, if you have multiple sentences, as you typically would have in a large evaluation, how do you compute this brevity penalty? So you basically sum for each sentences. So let's say आपके पास 10 examples हैं. उन 10 examples के लिए आपने हर एक के लिए R1 और C1 निकाल लिया, R2, C2 निकाल लिया, R3 C3 निकाल लिया up till R10 or C10 निकाल लिया. So the final R is basically R1 plus R10, and similarly the final C is C1 plus C10. For each of those R's, R1 and C1, we will use the same logic, meaning that we will choose the length R that is closest to C. And if the overall R is bigger than C, then we will apply the brevity penalty, otherwise we will not. If C is greater than R or even equal to R, of course, when it's equal to R, the brevity penalty would be 1. If C is equal or greater to than R, we do not apply the brevity penalty. We only apply when C is smaller than R or less than R. So far I have used unigram. Of course, unigram is would capture words, but it won't capture fluency, meaning the usage of words in proper grammar or in proper language. So usually we will also use higher order n-grams. So we can use 2 grams, we can use 3 grams, and we can use 4 grams. So usually we typically go up to the maximum of 4 grams. And in each of these cases, we of course we proceed in the same fashion. So for example, my C is, let's say, D cat mat on, let's say. So if I use bigram, what are my bigrams? So my first bigram is a D cat, the second is cat mat, and the third is mat on. So now these are the bigrams that will match in the reference. So D cat appears in the reference, cat mat does not appear in the reference, and mat on does not appear in the reference. So in this case, for this particular example, the precision would be 1/3. ठीक है? So ये bigram के लिए इस तरह निकालेंगे. इसी तरह trigram के लिए भी and 4 grams. So sometimes we will report all of these blue scores. So in this case, this would be BLEU-2. So we report blue scores separately, meaning that blue 1, blue 2, blue 3, and blue 4. Sometimes we can even take the average of all those 4 and report just one blue. Okay. So of course, you can report the maximum information and make a discussion on the results rather than combining all those individual blue scores into just one blue score by taking the average. Okay. So this is the BLEU or Blue Score way of evaluating machine translation. This is based on precision, and more precisely the clipped version of precision. So if the generated candidate has multiple words, we only take that many words that appear in any particular reference. And then also at the end, we do a geometric mean and then add a brevity penalty, which penalizes small candidates that are generated, shorter candidates that are generated. So usually 4 blue score, blue 4 would give you a fairly good estimate of the true quality of the machine translation. But of course, this is based on exact matching, overlap. So that is, of course, an issue. You might have synonyms, so synonyms would not match. Okay. All right, so now let's quickly talk about ROUGE, which is a major, which is recall oriented. So this is recall oriented understudy for gisting evaluation. So this major is more popular for evaluating summarization or summaries, but it can be used for translation as well. So the idea is the same. You have a candidate and you have a reference. In this case, only one reference. So we don't have the option of having multiple reference. Okay? So only one reference is required. We cannot use multiple references. And as I said, this is recall oriented. Of course, variations of this also use precision as well, but the original one only use recall. So let's take an example. Let's say C मेरे पास था D cat और मेरे पास R था D cat sat on the mat. ठीक है? So this is 6. So in recall oriented, we look at each word in the reference and see whether it appears in the candidate. So in other words, the candidate here is the summary. The reference here is the full text. So as I said, this is used for summarization, more popularly for summarization. The reference here is the full text and the candidate is a summary. So we take each word. So how many, again, this could be one by unigram, bigram, and so on. So ROUGE 1, this is basically unigram. So what are the unigrams that we have? The cat sat on the mat. We can have 6 unigrams, and then we check whether each of those unigrams appear in the candidate. So D appears, cat appears, and then sat does not appear, on does not appear, D appears again. In this case, we don't have the notion of clipping, and then mat does not appear. ठीक है, तो ये फिर क्या हो जाएगा? 3/6. So this is the recall. So 3 words match with the candidate. So 3 words in the actual document appears in the summary. Okay? So D appears in the summary, cat appears in the summary, and D again appears in the summary. And of course, we normalize with the reference length, which is 6. That's why this is recall. Okay? So this is ROUGE. Of course, ROUGE has its variants. So we have ROUGE in general N, which is based on n-gram. Okay? We also have what is known as ROUGE L, which is based on the longest common subsequence. So longest common subsequence, we studied this when we are discussing edit distance. You have to align the two passages and then count the length of the longest overlap. They may have gaps between them. So you have to solve the dynamic programming problem for the alignment and then count the overlap, length of the overlap. So in this case, of course, you're also now considering order of words. Okay, so this is also commonly used. And then we have ROUGE. S is also sometimes used. This is based on skipgram. So skipgram usually meaning that, so you have a sentence, so D cat sat on the mat. So you can match, so the skipgrams could have 2 words with any number of gaps, any or 0 number of gaps between them. So for example, D cat is a skipgram. D sat is also a skipgram. D on is also a skipgram. D is a skipgram, and D mat is a skipgram. Of course, this is by 2 word skipgram. Okay, usually 2 words ही use किया जाता है practice में. So order is maintained, but we do not consider the gap between them. So we will write all the possible skipgrams in the reference and then check whether they appear in the candidate, and then of course compute the ratio. जिससे पहले हम निकालते थे. All right, so I think that's all for ROUGE. So this is recall oriented or recall based, and we have these variants, ROUGE N. You can have unigram, bigram, trigram, and so on. In general, n-gram, and you have also the ROUGE L, which is based on LCS. We basically find the longest common subsequence in the reference and then see whether it matches in the candidate. In other words, we do an alignment and take the length, and of course this is a final value. So ROUGE L is the final value. Normalized value आएगी आपके पास. And then of course ROUGE skipgram is you compute all skipgrams by 2 word skipgrams and then compute the recall. Finally, now all of those examples were word-based. So now we also have a character-based, which has become more popular nowadays. So character-based overlap. And the technique here is simply called chrF. F for F score, or you can also say chr precision, chr recall. Okay, so you can compute precision, you can compute recall, you can compute F score. F score, of course, is based on both precision and recall, and you can do it for various n-grams, character n-grams. So let me just explain the process. So first of all, why is character n-gram becoming more popular? A couple of reasons. One reason is word overlap is much harder because you may have a synonym, but character overlaps are more likely. And the second reason, which is actually more relevant, is that nowadays we often have but that may not be a big issue. Okay, so I'll skip that. So mainly because it is harder to match words. So matching characters would be much easier. But of course, we are not matching single characters. We will be matching higher order characters. And generally, we use a measure K, which is the max K-gram to be considered. Okay? And of course, K is greater than equal to 1. Of course, 1 is trivial or it's not recommended. 2 is even very small. So usually K is larger, 3, 4, or even 5, 3 or 4. Okay? So that's one thing. Secondly, we compute for all. So we compute for 1 gram. We compute for 2 gram until you compute for K gram. तो सारे के लिए हमने निकालना है. ठीक है? प्रिसीजन भी 1 के लिए निकालनी है, 2 के लिए निकालनी है, 3 के लिए निकालनी है, up till K, और रिकॉल भी निकालनी है. And then we average all of those. So for example, let's say आपने CHR precision निकाली 1. So CHR precision 2 निकाली, और let's say K3 था आपका, CHR precision 3 निकाली. The final CHR P would be simply CHR P1 plus CHR P2 plus CHR P3 divided by 3, the average. ठीक है. So this is the final CHRP. So इसी तरह आप निकालेंगे CHR. It would be basically CHR_R1 plus CHR_R2 plus CHR_R3 divided by 3. ठीक है. ठीक है. And then, so we have now the average of the precision and average of the recall for unigram, bigram, and trigram. And now we can compute a chrF, which is F score, which is harmonic mean. So, and this harmonic mean, we use a slightly different weightage in practice. In general, the formula for this is what? 1 plus beta square. Okay. We have CHR precision into CHR recall, okay, divided by beta square into CHR precision plus CHR recall. ठीक. तो ये in general F score का formula है, but for many of the applications that we have seen in practice, people use beta is equal to 2 for machine translation evaluation. Of course, for most classification cases, we usually use beta as 1. But for, in this case, we are using beta is equal to 2, which basically means that we are giving greater weightage to precision. ठीक है. So if you actually कर दें तो उसको क्या बनेगा ऊपर 2 है ऊपर 5 हो जाएगा 5 into CHRP into CHRR divided by we have नीचे क्या होगा नीचे भी square I think 4 हो जाएगा नीचे CHR precision plus CHR recall. So this is the formula that is commonly used to combine CHR and CHP. So this measure, as I said, has become more popular in the more recent years, last 2-3 years, as opposed to Bleu. Bleu was popular since the 1990s, but this has become more popular nowadays. It uses character-based overlap. It uses both precision and recall. So both precision and recall. And then also computes the F score. And this F score is computed by weighing precision slightly higher than recall. And also, we consider all n grams up to a maximum k gram, and we take the average value as the final value. Okay, so that was CHRF, or character-based F score. So now let's move on to all of these measures were based on overlap of words or overlaps of characters between the reference and the candidate. And of course, if it was precision, we took the candidate and found overlap in the reference. If it was recall, we took the reference and found the overlap in the candidate. Okay. So let's discuss some other measures that have been used even more recently, last 2-3 years. So these are, you can say, similarity based, or you can say prediction based. And the main motivation for this is that overlap would not occur even if you are using a synonym. So for example, if you have, I gave the example before, so for freezing, for example. So freezing may be used in the reference, and maybe in the candidate you use the word cold. So both of them are very similar words when used in this similar context. So, but if you do a simple overlap, they will not match, and you will not be counting this as a correct or as a good translation. So this was the main motivation for using these other measures that are not based on overlap, but based on some notion of similarity or relatedness. Of course, one way to avoid this issue is, of course, you can check for synonyms as well, but that is quite cumbersome. So हर एक word का आप synonym भी check कर लें, let's say I don't know. So so freezing and cold typically would not be synonyms if you look at linguistic perspective. So cold ka synonym kuch aur hoga probably, although you might have a word freezing similar to it, but exact synonym shayad nahi hoga. So synonyms mein, for example, let's say good kahin likha hua hai or like kahin aa raha hai, so this might be synonym. So if such things, you can of course do this manually using a dictionary or a resource like WordNet. But nowadays we will move towards similarity based measures. So I'll just discuss briefly two techniques. The first technique actually is based on prediction. So what do we have? We have a candidate and we have a reference sentence, right? So we have a candidate, which is the generated text, reference is the true text, and for each of these, we also have a rating. Okay? And or we would like to have a rating. So how good is this R as a translation of this C? Or you can say, I would say rating के बजाय score कर लेता हूँ. ठीक है? So let's say you just label some few examples, a few hundred examples by humans. ये data set आप बना लें. So create basically a data set of C's, R's, and scores. Okay? So of course, this would be a small data set that is and basically human labeled. Okay? So once you have labeled, you have this labeled data set, you can train a classifier. And we can use a transformer, for example. So transformer. So you can use a transformer. So for example, in transformer, you can have, so use a transformer to learn the score. Okay? So the classifier, the transformer would start with a, let's say, CLS token, a class token. And then you have all the tokens for C, which is your candidate, all the tokens for C. I've just written one C there, but there will be multiple words in C. And then you have a sep token, separator token, and then you have all the tokens for R. तो ये आप ट्रांसफॉर्मर में आप देंगे और जो CLS टोकन का जो आउटपुट होगा, which is Y corresponding to CLS, you pass that through a classifier, or in this case score है तो regression model पे आप classify करके वो use कर लें prediction के लिए. So you can now learn a model, in which case CLS का जो output है, it would give you the score. ठीक है? Of course हमने transformer क्यों use किया? Because we can track relationships between the words in R and the words in C. And also because we can use richer representations for each word in C and each word in R. Richer representation का मतलब क्या है? Embeddings हम use कर सकते हैं, या even contextual embedding use कर सकते हैं, which we are going to discuss next for these words. ठीक है? और जो CLS token का जो A आएगा उसका, and after that A through a output layer Y जो आएगा, that would give you the score. And of course, you can train this using the training data that you have, which has C, R, and the scores. So once you have trained this network, you can now simply use it to find the score for any two C and R's. Okay? So simple as that. तो आपने जब एक मॉडल ट्रेन कर लिया, so now you simply give a C, you give an R, and the transformer will tell you the score. So this has been found to be fairly accurate in practice as long as you have a decent size of training data. So of course, decent size would be kind of difficult. I would say about a few hundreds से आप शुरू कर सकते हैं, for let's say English for example. Because since usually we'll be using a pre-trained network transformer, उसमें language information पहले ही है, you just fine tune it to this task, maybe using 500 or 1000 labeled examples. Once you have fine tuned it, by the way, pre-training fine tuning हमने next discuss करना है, so just hold on. So once you have done that, you can use it to make predictions. So this is a good way. Of course, this is based on similarity. Within the transformer, we are capturing similarities. You can also use, of course, this technique is popular. You can also do explicit similarity matching as well, without using a classifier, without using any labeled data set. So in this case, let's say you have a C and you have a R. So for C, you use, for each of the words in C, you find the embedding. So let's say C मेरे पास था, so let's say D cat, और R था cat on mat. ठीक है? So what do we would do? We will take D की embedding मिल जाएगी, आप word to vec use कर सकते हैं, contextual embedding use कर सकते हैं, whatever you have. So D का word जो है, now you find the word in R that is most similar to D. And of course, and the similarity should be greater than some minimum threshold. If you are able to do that, then you have this match. You call this a match. ठीक है? Minimum threshold से भी ज़्यादा होना चाहिए, और yeah, minimum threshold से ज़्यादा होना चाहिए. So, and if you are matching C with R, this would be precision. So इसी तरह cat को आप match करेंगे precision, and then you can compute your Bleu score or the other scores that we have talked about earlier. But now you are matching based on embeddings and cosine similarity between those embeddings, not simple character overlap or character matching. Okay? So this technique can also be, usually this is done in a greedy way. So D आपने लिया, D की embedding है, अब देखा कि reference में कौन सा सबसे close है उसके साथ. In this case, I think मेरे ख्याल से किसी के साथ नहीं होगा, because there is no determiner in the reference. Cat on mat मैंने लिखा है. ठीक है, so probably D match नहीं होगा. Then cat, of course, would match with cat. This will be an exact match. So you get 1/2 as the precision. So let's say कोई और आपके पास कोई sentence है, let's say cold out there. So in this case, if you take the embedding of cold and try to match it with the embeddings in the reference, it will match quite closely with freezing. So this would be a match, and basically greedy match करना है जो सबसे ज़्यादा हो रहा है. So एक match हो गया. Of course, it should be higher than a threshold. So then if you look at out will probably match with outside. So आपके पास दो match तो हो गए. ठीक है? And then there, of course, would match. At least you get a precision of 2/3. But if you did exact match, the precision would be 0/3. So this is one other way of doing matching using embeddings. ठीक है, time काफी निकल गया actually 10:51. Okay. All right. So, okay, so this was about evaluation. A few other things regarding machine translation. So usually for transformers, so whenever we are using transformers for machine translation, we usually use what is called subword tokenization. So we had discussed subword tokenization before, for example, BPE, byte pair encoding. So another subword tokenization is word piece, which is based on unigrams. So BP is exactly based on n-grams. It doesn't use any language model, while word piece uses a language model, which is a unigram language model. So in any case, both of them are relatively simple, straightforward. So subwords, of course, why are they used? Because you can handle the issue of out of word vocabulary, okay? And also controls the size of the vocabulary. So if you did not use subwords and you use each distinct word as a separate word, then the vocabulary size would be very large. So it also controls the size of vocabulary, which in turn controls the size of the network. Remember, जितनी बड़ी vocabulary होगी आपकी, to some extent, of course, उसका network, if you have embedding layer, तो network का size भी उस पर depend करेगा. ठीक है? So that's one of the reasons that we use subword tokenization. The second thing for machine translation is we basically oftentimes tokenize, or I should say, a common vocab for both source and target. So instead of having a separate vocabulary for the encoder, which is the source, and a separate vocabulary for the decoder, which is the target, we have a common vocabulary and have the source also consider the target vocabulary as well. Of course, उसमें target words तो नहीं होंगे, but कुछ हो सकते हैं थोड़े से, which I'll mention shortly. So इसके दो reasons हैं. एक reason तो ये है कि why do we do this? For example, there are some words that simply move from source to target, and those words are like named entities, for example. So let's say किसी का नाम है source में, if I have उर्दू में मैंने आसिम यूज किया हुआ, तो इंग्लिश में भी वो आसिम ही रहेगा. ठीक है? So that's why we use a common vocabulary. ठीक है? So we'll need to have that word आसिम in the target also. So let's say कोई शायर है लाहौर, उर्दू में यूज किया तो इंग्लिश में भी वो लाहौर होना चाहिए. ठीक है ना? तो कॉमन वोकेबुलरी एक वजह इसकी ये है. So दूसरी वजह जो है which we use, of course, if the script is different, let's say Urdu or English, of course Lahore Urdu में different होगा और English में different होगा, but still you will have in both cases Lahore. And you can actually match the two using some additional processing. कि ये Lahore वही वाला Lahore in the different script. Okay, that's one reason. The another reason is what we have in some neural network you can have you can do what is known as a copy tokens from encoder to decoder. So so let's say decoder कोई एक vocabulary एक distribution generate करता है over the vocabulary, and you're not able to find any word with very high probability. सारों की probability let's say बहुत low हैं. So rather than outputting some low probability word as a translation, you might want to simply move the corresponding word from the source language to the output language. So that is copying a token from the source language to the output language. So मतलब हम ये English उर्दू में तो बहुत करते हैं. For example, so for example, if I give an example like, so किस time पे class होगी, let's say. So time is actually a English word. It's not an Urdu word. So maybe when we were generating the word for time in the Urdu vocabulary, we were not getting any word with a high probability. So instead of using that word, we simply copied the appropriate word from the source to this particular position, which is time. So copying words is one technique that is often used in many machine translation techniques. The other, as I mentioned, is have to have a common vocabulary. And by the way, copying would only work when you have a common vocabulary. Okay. Okay. Usually, the training data for machine translation is called a parallel corpus. So what is a parallel corpus? You have a source text, and for each source text, we have the target text, meaning that you have pairs for training data. You have a sentence or a paragraph in, let's say, Urdu, which is a source text, and the same paragraph or sentence in English, which is a target language. So you need to have such pairs to train your neuro translation model. And oftentimes you'll need lots of such data. Usually this training data would typically run into the millions, because we are not learning a simple classification problem. This is a more of a generation problem. For generation problems, you need lots of data. So this is called a parallel corpus. Sometimes this is also called by text. मतलब two text है. But oftentimes, of course, many parallel corpora are available on the web for many pairs of languages. So you can use those if you want to train a machine translation model. One important aspect in developing a corpus is that you need to have alignment between source and target. So what happens typically, let's say आपके पास उर्दू में एक document है, वही document English में भी है. But the problem arises that the first sentence of Urdu may not be the one that is translated as the first sentence of English. Okay? So the first sentence in Urdu might be translated as the second sentence in English. तो आपने जब parallel corpus बनाना है, तो first sentence of Urdu आपने pair करना with the second sentence of English. अब ये, this is the alignment problem. We want to align the two corpora. So this is actually a difficult problem. So this is the main issue while we are developing a corpus. So alignment के लिए भी कई तरीके हैं. People often use embedding type of approach, जो हमने पीछे evaluation के लिए भी use किया है. So you can find the embedding of each Urdu sentence, each English sentence, and then compare the embeddings and do a greedy match. जिसके साथ सबसे ज़्यादा match हो रहा है, we say that this Urdu sentence correspond to this English sentence. ठीक है? So alignment problem has to be solved if you want to develop a big corpus for a source and a target language. And of course, as I said, many parallel corpora are available on the web, and most of them are for resource-rich languages like Chinese, English, French, Spanish. These languages have lots of resources available. For example, for most of the European languages, one good resource is the proceedings of the European Parliament. So the proceedings of European Parliament is translated in all the European languages. So you have that corpus available, and I think it's also aligned. You can use it for training a machine translation model. So for languages like Urdu, we have little or few corpora available, and so that is a challenge. And to develop such corpora is, I think, a challenge and also very rewarding. So it could even be a research project for developing corpora for Urdu. Okay, one final comment before we end machine translation, the issue of back translation. So by the way, all of this is from chapter 10 of your textbook. So I'm following, I think, quite faithfully this section or this chapter of the textbook. So इसमें कोई ज़्यादा extra material नहीं है. So back translation, what does this mean? So this is more appropriate when we don't have large amounts of parallel data or by text available. So let's say आपके पास आपने let's say Urdu English translation करनी है. So English is the target, Urdu is the source, and you don't have much data for Urdu translated to English. And also, yeah, I mean, you don't have much by-text data, but you have monolingual data. English का data आपको सिर्फ English का data काफी मिल जाएगा, ठीक है? And also Urdu का भी मिल जाएगा, but let's focus on English. So let's say English का data आपके पास काफी है. So what you can do is using any small data set. Remember, English mono data is huge, but Urdu is small. Okay? So what do you do using some small corpora and some small model, which you train, of course, for that you do need a parallel corpora. But using that, you generate Urdu from English. So kind of back translating. Although our goal was Urdu to English, we are actually doing back translation from English to Urdu, because English was available as a single language, as a monolingual language in large amounts. We translated that back to Urdu. So now you have lots of Urdu data, and also we have lots of English data from this simple back translation. But it turns out that if you just augment your original human labeled Urdu English data with this back translated data, your translation improves because your data size has increased tremendously. So this is a very quick and easy way of doing this. So people have also done this by bringing intermediate language in between. For example, English को आपने French में कर दिया, French से आपने Spanish में ले गया इसको, और Spanish में बाद में वापस English पे ले आए, ठीक है? In this case, of course, you don't have a different language, but again, now for some applications where you want different examples of English, आप इस तरह generate कर सकते हैं. Intermediate कुछ और language में translate करें, वापस English में ले आएं. So for example, let's say paraphrase detection आपने का corpus generate करना है, तो आप English का आपके पास data set है, उसको आपने Chinese में किया, फिर वापस English में ले आए, तो ये आपके पास एक paraphrase आ जाएगा. उसको आपने Spanish में किया, फिर वापस English में ले आए, एक paraphrase आ जाएगा, ठीक है? Or maybe you can use multiple languages in between. Spanish में किया, French में किया, फिर English में ले आए. So using translation, you can generate additional corpus as well. Of course, in this case for paraphrase detection, in the previous case for translation. So I think with that, we will conclude this chapter. So the next chapter is on contextual embeddings. And transfer learning. So this is actually chapter 11 of your textbook. So of course, इसमें कुछ concepts हैं, but ज़्यादा इसमें depth नहीं है इस chapter में. I think next lecture में फिर होगा, अब time आज खत्म हो रहा है. इसमें of course एक model जो हम discuss करेंगे, which is the basis of this chapter, is called the BERT. So which is bidirectional transformer. Remember previously we talked about a causal transformer, a backward looking transformer. So a bidirectional transformer can also look forward. So bidirectional encoding representation. This is actually the acronym BERT. Representation using transformers. Okay, so this is BERT. But main thing is usually a bidirectional transformer. So previously we had talked about a transformer which only looked at the previous context. It did not look at the subsequent context. So the bidirectional transformer can look at the subsequent context as well. And the first time this model was proposed was in 2019. So again, it's quite recent. And since then, BERT has become extremely popular. So I will discuss this, of course, next time, but one other concept, the concept of transfer learning. So we had already talked about transfer learning previously. So remember, we talked about word2vec. So word2vec was trained on some large corpora of text. Let's say if you're talking about English, a huge English data set. And what do we get at the end of the day? For each word, we have a representation, a vector. And that vector can be used in any downstream application, like for sentiment classification, for topic classification, for language modeling, and so on. So this is also an example of transfer learning, because we had trained something or learned something on some other data set and then used it on some other data set or on some other task. So anytime when we use knowledge from a different task to a different task, that was transfer learning. So we learned word2vec from a huge corpus. This was a separate task. And then after we have learned these vectors, we use these vectors for, let's say, sentiment classification, which is a different task. So this is an example of transfer learning. Okay. So thirdly, of course, we talked about word2vec. Word2vec are called static embeddings, meaning that once you have learned these embeddings for each word, let's say आपने word live LIVE के लिए embedding learn कर ली, तो वो एक fixed embedding है. Once it has been learned, it doesn't change. You can use it, of course, in downstream application, but it doesn't change. Whether that word live appears in a particular sentence or in a different sentence. While in the case of contextual embedding, the embedding would change depending on the context in which that word appears. What happened? Okay, so contextual embedding में, let's say I live in Lahore. What happened? Next second. So I live in Lahore and I watched the match live. The embedding for live would be different for live. But if you use static embeddings, then of course it will be the same. But if you use contextual embedding, वो context को देखेगा और live के लिए different embedding देगा, live के लिए different देगा. So this is the idea for contextual embeddings, and we'll discuss this in the next lecture. So I'm planning that probably next lecture को ही मैं last lecture बना दूंगा, because we still have maybe 1 or 2 lectures left. But उनमें फिर नया topic शुरू करना पड़ेगा, and I think it would turn out to be difficult. And I think most of you are also in the Ramadan mode, or exam भी आ रहे हैं, so I will probably stop in the next lecture on Thursday. ठीक है? Unless if someone has a major objection. ठीक है?